Hello, so I'm Chris Ellis, the head of technology at Next Team, and I'm going to be talking about fun with UUIDs. So, this is a talk about the kind of pitfalls and advantages of using UUIDs as primary keys instead of just standard database sequences. So, this kind of talk is really for any kind of application developers who might be working on multi tenanted, say, SaaS applications, where the advantages of using UUIDs will probably be out benefiting the problems that they cause. Okay, so now let's have some fun with UUIDs. So first off, a little bit about me. So I tend to go around calling myself a bit of a an IT jack of all trades. I'm kind of as comfortable dealing with and building hardware as I am kind of designing and building front ends and everything in the middle. I spend most of my time working as kind of application kind of developer and architect around kind of back end systems and databases. And over the 20 years I've been working with Postgres, I've kind of worked on a whole range of different projects from search engines to subscription systems and smart energy analytics and IoT platforms. And to kind of really start with, let's first off talk with about what is a UUID and what do we mean by one. So, first off, the acronym stands for Universally Unique Identifier. And most people are kind of used to seeing them like this, where we see them as a 36 string, 36 character string of hexadecimal characters with a few hyphens sprinkled in. Now, obviously, this is actually just a 128-bit number or 16 bytes of data encoded as hex in this particular form. So, actually, under the hood, it is just 16 bytes of data and a 128-bit number. And to Postgres, that's exactly what it is. Now, in general, most people are kind of used to using and seeing what are called version 4 UUIDs. So inside the UUID itself, there are two nibbles which provide certain bits of information. So there's the version nibble and then the variant nibble. So the version here kind of captures the particular version scheme of this UUID structure. And as I said, the one that people are most used to coming across is a version 4 UUID. And this is what Postgres supports out of the box. Now, a version 4 UUID is basically just a complete random number. The rest of the kind of information there, the 120 bits of non kind of version information, is just a randomly allocated number. There are very little control or concepts about how that should be allocated. Obviously, most systems will want to try and use some form of cryptographic random number generator to do this, but it is just 120 bits of random number. So using this in Postgres is really no more complicated than if we were to use any other data type. It is just a data type as far as Postgres is concerned, and we can use it just like we can a big int. So we can declare it as the primary key of our table in just the same way as we would normally. UUIDs in Postgres are still fully compatible with B tree indexes, and you can use it just as you would your standard kind of serial. And you can't necessarily auto-generate these in as such like you can with using the big serial data type, but fundamentally they are just a data type as far as Postgres is concerned. And we can use them for foreign keys, we can join on them, we can query on them, we can use them in all sorts of different ways, just as we would any kind of other data type in Postgres. So let's go and talk about kind of what are the often cited problems with using UUIDs. And we're going to start with the really obvious one, just the size. They are twice the size of a 64-bit number. Um, and that obviously is going to have some form of impact on you. It's using twice the storage space inside Postgres to store that information. And in places, that's not really necessarily always a massive problem, right? But in certain situations, it might be. But at the end of the day, right, the kind of data in your table is going to be predominantly taken up by the contents of your row as opposed to the identifier of your row. So the size of it is also kind of like, frankly, a minor disadvantage, but later on actually can maybe be a significant advantage to your system and application. And what's more important is most of the kind of problems we see with UUIDs come from the fact that they are by default and at the moment randomly allocated. And most of the problems comes from this random nature of them as opposed to, say, anything inherent about it as data type. And this is where it's really important to understand that on the surface of this data type, it's maybe not as simple as just other things. And, there are multiple ways to construct and use that space, which is the kind of importance here. Now, From a perspective of indexes, the kind of random nature of it is going to create a bit more churn than it would if it was sequentially kind of stored in your kind of system. It's going to take a bit more kind of work because every time we're going to insert something, it's not necessarily going to go into the same page. Whereas the nice thing about kind of a sequential number that's always increasing, then it's going to roughly end up in the latest page inside your index. And this kind of like natural correlation that we tend to have but in with sequentially allocated index keys and indexes is actually quite advantageous. And Postgres has certain optimizations, specifically the free space map, where that correlation is actually quite important. And there's a very good blog post about this, and we can take a very simple query to kind of look at the impact of that, and then we can use that as a bit of a benchmark to see if we can actually get better or more useful performance out of UUIDs by constructing them better and then still having the advantages we want from them. So we're going to start off with a very simple test case throughout this kind of talk. We have a table which has an ID, primary key. We have basically a big int version, and then later on we have a UUID version. And then we have a value, which is just a text string. And for the purposes of everything in this talk, it is a 500 byte kind of string, which is the same on every record. And that's there just to represent that in most normal real world situations, you're going to have some data in your kind of row as well as just your ID. So we're going to try and keep these benchmarks and tests semi-realistic. So obviously the UUID variant here, the only change in this particular table structure is the data type of the ID column. Now, if we go and take a index-only scan of the ID, we can start seeing the impact of this free space map problem. So first off, actually, let's just have a quick look at the size of the kind of tables, and you'll see that actually the bulk of the kind of table space is used just by the row data. We don't have a significant impact, maybe at most 5-10% kind of extra space used, but that's going to vary deeply depending on the size of your data. And the indexes are probably almost double the size, but we kind of expect that given the identifier is double the size. And then, so let's then kind of look at the kind of free space map implications of this. So if we just do an index only scan across that integer sequentially allocated table, we'll see that we don't really kind of hit more buffers than we kind of really expect to kind of see in that index. And that's because kind of we can cheat and use the free space map to check the visibility of those records that the indexes point to. So a key problem here in Postgres is that indexes don't have tuple version visibility. However, what's fascinating is if we do this exact same query but against our randomly generated UUIDs, we see a significant problem where we have an order of magnitude more number of buffers that have to get checked. And this is, again, because stuff's not neatly correlating between our free space map and our index. And it means that as processing that index scan, we've got to go and check a lot more active buffers. And that's got a cost of pulling them in and out of memory, even if they're in shared memory. Now, what's fascinating is if we do the same thing, but on a 64-bit integer column that's been randomly allocated, we get exactly the same problem. So this is a very simple way to demonstrate that some of these optimizations are not necessarily about the data type itself, but about how we're using that data type. So the fact that this kind of data type has been randomly generated here, and the fact that it's still 64-bit number, it's the random nature and distribution of it that's causing the bulk of these kind of problems in some of our performance optimizations that Postgres has. So with this in mind, why do we want to use UUIDs, right? Why do we want to go to this effort? And this is kind of where this sort of talk came from, was a discussion I had with somebody explaining like actually the reason I like them and why I kind of use them. And there's a number of advantages about this, which is kind of there's some security advantages here in web apps. Exposing sequential IDs is not great. Like nobody wants to be able to just increment a number on a URL and be able to download somebody's photos. And this is not really necessarily a full security argument, but it's definitely some form of like security through obscurity. But being able to just use UUIDs here makes our kind of URLs way more difficult to guess and just kind of cuts out a range of problems easily just by using a different data type. And at the end of the day, 128-bit numbers are very big. There's an awful lot of combinations. It's very hard for people to try and guess them, brute force them, and we get a kind of number of advantages from that. Another thing that I think is actually maybe not thought about quite so much is that a big downside database sequences is, by definition, they can only be generated by the database. So whenever I want to allocate an ID to something, I have to go and call the database to insert that data, and then often, and this is a nice advantage of Postgres, say returning ID. Now, the great thing with UUIDs is I can generate them in the application layer, and I can generate and create them across all nodes in my application layer because by definition, they are universally unique. Now, that's kind of maybe doesn't seem like a massive advantage in places. It can reduce some bottlenecks here and there, but actually there's some kind of latency gains you can get by this. If you're in a situation where you're inserting a parent record and multiple child records, or you have a kind of complex nested data structure that you're storing, you need to issue multiple insert calls. Then if you've got to go and insert a record and then wait to get the ID that's been given back to be able to insert the second record, you now actually have a kind of latency problem here. Whereas actually the great thing we can do is if the application can generate those IDs, we can just issue all the insert statements in kind of one latency hit across the network. But it's just a kind of like small little thing where those kind of little things actually, as an application developer, do add up and can make your application feel more responsive, even the fact that you're using a bigger identifier. And that kind of, again, the advantages of these being like universally unique is great for situations where you might say have geographically dispersed data. So if you've got data across 2 different European regions and you want to kind of actually be able to pull that data back together in a data warehouse at some point in time, UUIDs are great at knowing that realistically you're unlikely to collide if they're random, and if you're designing them carefully yourself, you can guarantee they won't collide. And this can be a massive benefit to sharding. And especially if we do what I like doing, which is encoding additional information into UUIDs. So, and somebody pointed out, this is maybe the hardware developer in me, but I like to bitwise encode information into UUIDs. I just see them as a 16-byte data structure that I can do something with if I know what I'm doing. And a lot of my applications across the years have been multi-tenanted. And what we've done is we've encoded the tenant information into the UUIDs. So by just having an object identifier for a record, we know which tenant it's for, and we can then go and say select a shard to go to or talk to, or we can get a whole kind of routing layer sort of for free just by using the size of UUIDs to be able to encode this information. Or for example, we might put a cluster ID in there for some certain distributed systems. Or we could maybe get smart and use some form of partitioning information inside that kind of data type, maybe for, say, some certain kind of IoT or monitoring type platforms and systems. And then another one I quite like doing is just the ability to be able to know that this ID is like this type of record. So by just being able to put a simple tag inside your ID that says, actually, this ID is for a insurance claim and this ID is for a repair against that claim, can be kind of a massive advantage in certain situations where you might have systems where people have to type in these form of numbers or maybe a slightly smarter encoded form of that number. And you can make some kind of quick and simple decisions in your application there based on that kind of simple information and metadata that's inside your kind of identifiers. So as a simple example of here, right, let's just say a very simple multi-tenanted UUID setup could be, we make the upper 64 bits of the UUID, so the most significant bits, to be our tenant identifier. And then the lower significant bits of our UUID are just a 64-bit random number. So we've still got those kind of nice properties of them being kind of random and secure and hard to guess, but they're all namespaced by tenant, so we get some nice advantages routing. This is a very simplistic approach that's kind of worked perfectly fine in some of my kind of smaller systems. But this is where we can start getting some advantages out of it. But how do we then sort of trade this off with the performance concerns we've talked about? And how do we try and solve those kind of problems and get the best of both worlds? So how do we balance those different trade-offs together? Well, there's a new upcoming standard that's been kind of sort of ratified more the last couple of years called UUID v7. And these are effectively time-bounded or time-ordered UUIDs. So the upper 48 bits of UUID v7s are effectively an epoch-based timestamp. So it kind of gives you millisecond granularity of time. And then the rest of the ID, again, is just randomly allocated, or can be. And this is actually great for fixing the bulk of the problems we saw in kind of Postgres index performance, because we get that kind of natural kind of co-location of information again. and that correlation between where data naturally falls within our table heap and therefore our free space map, and also the index. And as part of doing this talk, to some extent, I've been trying to formalize this kind of UUID schemes that I've used across a number of applications and actually just document this and share this a bit wider. So I decided to come up with a fun name for it, which was Fluid, Flexible UUIDs. And this is just a really simple version of using what's called a version 8 UUID, which are custom UUIDs that you can design your own schemes for. And this is, not necessarily perfect for everybody, and you might want to design your own for certain situations, application cases. But this is a great kind of getting started, and you can use these kind of approaches and how I designed them as potentially a shortcut, or use them directly in your system. So hopefully we'll have some kind of Postgres extensions to use and some kind of application code to make this a bit easier. And I've got two main forms of this. I've basically got a multi-tenanted UUID and then kind of an extended time version. And the idea here is that we still have a time component in there, so we still kind of play nicely with Postgres' indexes. And then we've got the information encoded in there that we can make useful to our application, such as that tenant identifier, some information about the entity, but then again, that random identifier that I kind of want. So we can take these and let's just kind of rerun our same performance benchmark. So if we take that kind of extended kind of format where we've got 32 bits of time information there, so we've got second granularity time information in there, then you can see we don't really run into that kind of shared buffers problem that we were seeing with the randomly allocated UUIDs. And this is very comparable to the performance you'd get if you just used UUID v7. So we kind of can see we've solved the biggest problem here just by actually making the higher order bits of the ID still being time bounded. And of course, right, if we talk about pure security context, there are situations where we don't necessarily want to leak this time information, but if you're really that sensitive about your IDs and you're in that particular use cases, you should probably not be exposing them at all. Now, the multi-tenanted version in the benchmark doesn't do quite as well, but we still don't see the kind of catastrophic kind of randomness that causes the problems. And then this is much more dependent on how many different tenants do I have across the data set within the benchmark. And maybe we can look at kind of sizing that, the amount of space we use to store the time correlation to kind of still fix and improve that. So these multi-tenanted UUIDs are actually only got hour level granularity. And maybe we'll need to spend a bit more space to try and fully solve the performance of this, or keep it at least at a reasonable, so it's not too much of a performance degradation for people. So let's just take a quick look at, well, what's the actual impact of my application from a perspective of insert performance if I was to store these. So I wrote a quick benchmark. I'm going to insert 10 million records from Java. It's fairly quick code. It's not the most optimized. But this is just to prove that actually the performance degradation is not that significant. We may be talking about, in the best cases, a 10% performance loss. And so again, this is a situation where all the records are 500 bytes, and we're starting from an empty table with an empty index. So we're not even bothering to create the index afterwards. And we can see here that the time to insert our kind of like multi-tenanted UUIDs is maybe only 10% slower than our standard big use case. And actually here, I suspect the performance difference we're mainly seeing here is just the extra pressure on generating lots of random numbers for this particular benchmark. And of course, it wouldn't be one of my talks without a nice bit of Postgres stored functions. And I also just want to prove that even in just pure SQL, that we can generate these kind of structured UUIDs inside Postgres. Now, we've got some tricks going on here that we're basically relying on the fact that the way we structured these identifiers, everything is aligned to nibbles. So we can actually just manipulate these as strings because we don't have any kind of bitwise functions to manipulate UUIDs directly. So we can just kind of, maybe it's not the most optimal approach, but in situations where you can't install custom extensions on, say, managed service providers, this kind of just proves you can still do it, and the performance isn't that terrible. It's obviously going to use a bit more CPU, but you can still use generate series with this without it being too much of a problem. And then, of course, let's want we want to do the other side here, which is let's decode these identifiers inside Postgres as well. So we can take these identifiers and we can parse them. And again, we can just use those simple tricks of, well, we're just going to slice up the string, pull out the hex character we want, and then convert that hex character to a number. So we can easily extract the time information from these UUIDs, and we can extract the tenant information from these UUIDs. And we can do that inside Postgres, which then means we can say do something like this, which would be to query our tables and find all identifiers for, say, a particular tenant. Now, that's a fairly straightforward kind of thing where we can just call that function on there. And obviously in this particular situation, it's not the most optimal because it's going to do a full table sequential scan because we're going to call a function on every row. But again, this is where Postgres is awesome, and we can just use a functional index to actually now just index the tenant information. We don't actually have to have a tenant column on a table. We can just build an index where we need it and pull that information out of our identifiers. And then obviously up in our application land, we can use that tenant information that's built into our IDs to do sharding. So we can just decode the UUID that we've got in our request, select the kind of shard for that tenant, and then go and connect to that shard. And this is like so simple and so much of a benefit for certain applications where, especially SaaS applications, where you want to try and have some form of distribution. You don't have cross-tenant kind of connections within your data model. And so it's actually nice and easy to shard stuff per tenant. And then again, because we structured these IDs using the time portion as the most significant bits of the UUID, we can actually then use the fact that there is still some time correlation with our identifiers, and we can actually query these identifiers based on time. Because from Postgres' perspective, these identifiers are just 128-bit unsigned numbers. They still have some form of order guarantees. A bigger UUID is still bigger than a smaller UUID. All that not necessarily seems so obvious. It's still true. And so we can actually use that. And so this particular query here, whilst those UUIDs might be difficult to understand what they actually represent, is querying for like a 5-day period on the start of these kind of the epoch of these IDs. And we can kind of use that kind of tricks to then do partitioning. So we can time-based partition just with a UUID column. So as a simple example here, we're going to take our very simple table and we're going to remove the primary key because we're going to partition by ID. And then we're going to say we're going to partition by the range of that ID. And then we can create some partitions against that kind of main table and this is where like a helper function to build those IDs from a timestamp makes it a lot more easy to understand what's going on. And we can effectively say here, well, we're going to create a partition for each month or each quarter or whatever, each year, whatever makes sense to your particular data scenario. And we can then just partition and based on that ID by saying, well, we know it's going to be greater than this value and less than this value. So thank you very much for listening. And if you want to find out more about that, go and check out fluid.dev. And there's kind of a bit more information about these kind of different UUID schemes I've got and how you can maybe go about using them.